Welcome back to the deep dive. Today we're kind of pulling up a stool in Kesser and Steen's garage lab.
Yeah.
Can you picture it? These two young, really curious minds surrounded by, bubbling carboys, that sweet smell of apples fermenting,
Oh, yeah.
turning Tante Grin's apples first into cider, and then the goal is perfect vinegar. It's like modern alchemy happening right there.
It really is.
So our mission for this deep dive is to sort of decode that alchemy. We're going to unpack the science behind predicting alcohol content, both before and after fermentation, which is, step one for the vinegar. And then we'll get into how they actually calculate the acetic acid in the final product.
Right.
Understanding that whole journey step by scientific step.
And it's not just a fun project, though it is fun. These calculations are absolutely crucial.
Right.
Not just for knowing what you'll get, but for quality, for consistency, even legal stuff.
Legal stuff.
Yeah, like in Denmark, vinegar isn't just any sour liquid. It has to be made a certain way, through fermentation. So this is about empowering you, the listener, with the know-how.
Giving you the confidence to turn raw stuff into something finished and know what you've actually made.
Exactly. With precision.
Okay, so let's start at the beginning then. Kesser and Steen, they aren't old enough to drink alcohol, but knowing its potential and then the actual amount, that's the first critical step for vinegar.
Absolutely.
And this isn't just for vinegar, right? Winemakers need this info super early on.
Oh, definitely. They're tracking maturity right in the vineyard way before fermentation. So how do Kesser and Steen kick this off in their garage setup?
Well, they mainly use density measurement, usually with something called a hydrometer.
Okay.
Now, here's the thing. It doesn't literally measure sugar.
Right. That's a common misconception.
It measures the total dry matter dissolved in the juice. Basically everything that's not water.
Sugars, acids, minerals.
Exactly. And that dry matter, well, the assumption is that the fermentable part of it gets converted into potential alcohol. It's like reading the tea leaves of the apple's future, you said.
Huh. Yeah, something like that. It gives you a prediction.
So they measure the juice density. What units are we talking about here? How does that translate to alcohol potential?
Okay, so Kesser and Steen, being in Denmark, might often use Oechsle. You write it as...
Oechsle, okay.
It basically tells you how much heavier the juice is than water because of the dissolved stuff. So say they get a reading of 84 cores.
84.
That means the density is 1.084 grams per milliliter. And here's a quick tip, a sort of mental shortcut.
Yeah.
If you divide that Oechsle number, the 84, by about 8.
Okay, so 84 divided by 8, about 10.5.
Exactly. Around 10–11% potential alcohol. It's a rough guide, but handy.
Neat trick.
Now, Oechsle is common there, but globally, you'll also see Brix, written as CS.
Brix, right. I've seen that on fruit juice sometimes.
Yeah. It's just another way to express that same concentration of dissolved solids, that dry matter. But Brix is basically a percentage scale.
Percentage.
Yeah, grams of dissolved sucrose equivalent per 100 milliliters.
Yeah.
So that 1.084 density, the 84 Oechsle, that's roughly 20.25 Brix.
So Oechsle, Brix, different languages, same story about the potential booze.
Pretty much, yeah. They both tell you about the starting materials potential.
But what's the absolute key step for them to figure out how much alcohol they actually made, not just potential?
The crucial part is measuring that density before fermentation.
The initial reading.
And then measuring it again after fermentation is totally finished.
Okay.
The difference between those two readings, that tells you how much of that dry matter the yeast actually consumed and turned into alcohol and CO2.
So it's the change in density that matters.
Precisely. It's an indirect measurement of the alcohol produced, but it's very effective.
Got it. Now, I'm guessing Kesser and Steen don't want to use up loads of their precious apple juice for testing, especially before fermentation. Is there another way? Maybe uses less juice?
Absolutely. They could use an optical tool, a refractometer.
Refractometer, how does that work?
The big plus is exactly what you said. You only need a tiny sample, maybe just a drop. It's cleaner, less waste.
Okay.
It works by measuring the refractive index, basically how light bends when it passes through the liquid. Again, it's not directly measuring sugar.
Well, it relates to it.
Exactly. It has an internal scale, a table, that correlates that light bending, that refractive index, to a Brix, or maybe even an Oechsle reading. So it gives you the same kind of density information as the hydrometer.
Clever. So hydrometer or refractometer, it doesn't matter which one they use?
Well, the most important thing, the absolute key, is consistency. You have to use the same method for your before reading and your after reading. If you start with a hydrometer, finish with a hydrometer. Start with refractometer, finish with refractometer.
Mixing them up would cause errors.
Big time. They measure slightly different aspects, and temperature affects them differently too. So consistency is paramount, which brings up an interesting point. Why do we always see alcohol listed as percentage by volume? Percent vol on the bottle.
That is a good question. I just take it for granted. Why is it volume, not weight or something else?
Well, think about it from a practical standpoint, for trade, for tax, even just for knowing how strong your drink is. Volume is just easier and more stable across different conditions compared to weight.
Weight changes with temperature, right?
Exactly. A liter is pretty much a liter, but the weight can fluctuate. So for centuries, volume percentage became the standard practical way to talk about it. It connects that lab measurement, that density change, directly to what you understand on the shelf.
Makes sense. So those density readings before and after using the same tool that unlocks the whole alcohol story.
It really does. It predicts and then confirms the transformation.
Okay, so Kesser and Steen have nailed down the alcohol. Mountain 1 climbed. Now, the next challenge, turning that alcohol into vinegar, and crucially, proving how much vinegar, how much acetic acid they've actually made. This is where titration comes in, right? It sounds very chemisty.
It is a bit, but the principle is straightforward. And it's elegant. But first, let's quickly define vinegar.
Okay.
Like we touched on in Denmark, it specifically means it's made through fermentation. The alcohol is converted to acetic acid by bacteria.
Not just diluted acid.
Correct. Chemically, though, the molecule itself, acetic acid or ethanoic acid, is the same whether it's in your 5% household vinegar or a super strong 32% cleaning version.
Gotcha. So Kesser and Steen are using titration to measure the yield, how much they made?
Exactly. They're doing a simple acid-based titration to find the concentration of acetic acid. This is a bit different from what winemakers often do, which is a total acid or TA analysis.
Oh, that.
TA measures all the acids in the wine: tartaric, malic, lactic, acetic, etc. Kesser and Steen are focused just on the acetic acid produced from the alcohol. Oh, another quick point. Acetic acid is volatile.
Meaning it can evaporate?
Yeah, a little bit might escape into the air, especially if it's warm or takes a long time. It can slightly affect the final number, so careful handling is good.
Okay. So let's simplify the chemistry. What's the actual reaction happening when they titrate?
It's a classic neutralization. You've got your acetic acid, Chisiros, in the vinegar. That's the acid.
Right.
And you react it with a hydroxide ion, OR, which comes from a base solution they add carefully.
Acid plus base.
Yep, gives you an acetate ion, which just stays dissolved, and water. So Chasio plus OR yields Kesco plus AH.
Okay.
The beauty of it is it's a perfect one-to-one reaction. One molecule of hydroxide neutralizes exactly one molecule of acetic acid.
1 to 1. That sounds important.
It's the key to the calculation.
And what base are they using? You can't just use any old base, can you?
No, you need something standardized. They're using a very precisely prepared, fairly dilute solution of sodium hydroxide, NaOH.
Sodium hydroxide, okay.
That's a strong base. Acetic acid, remember, is a weak acid. The salt formed, sodium acetate, just dissolves. But because they know the exact concentration of the NaOH solution, and it reacts 1 to 1.
The amount of NaOH solution they use tells them exactly how much acetic acid was in their sample.
Bingo. That's the core idea of titration right there.
Right, makes sense. So walk us through the practical steps. Kesser and Steen have their finished cider vinegar. What do they actually do?
Okay, first they need a super precise sample of their vinegar. They'll use a volumetric pipette for this, say exactly 10.000 liters. Precision is key.
10.000 mils.
Got it. Then they add a few drops of an indicator. This is a chemical that changes color at a specific pH. Crucially, it should be the same indicator they used when they first standardized their NaOH solution.
Why the same indicator?
So the color change happens at the exact same point of neutralization, the endpoint. Consistency again.
Always consistency.
Okay, next they take a burette, that long glass tube with markings and a tap. They fill it with their standardized NaOH solution and carefully set the starting level to 0. Then they slowly, drop by drop, add the NaOH from the burette into the vinegar sample, swirling gently.
Watching for.
That color change. They're looking for the exact point where the indicator just flips color and stays changed. That means all the acid has just been neutralized. That's the endpoint.
And they measure how much NaOH they use.
Exactly. They read the final volume on the burette. Let's say in their first go, they used 8.45 milliliters of NaOH.
Okay, 8.45 milliliters, so they have their numbers. 10.000 milliliter of vinegar sample, and it took 8.45 milliliter of NaOH solution, which they know is exactly 1.0000's normal strength.
Correct.
So how do they calculate the vinegar strength from that?
The calculation itself is pretty straightforward. The concentration of the acetic acid, usually expressed in normality first, is the milliliters of NaOH used, times the normality of the NaOH, divided by the milliliters of the vinegar sample.
Okay, so ml NaOH, X many NaOH, ml sample.
Yep. So for Kesser and Steen, 8.45 millio times 1.000 N divided by 10.845 N.
Exactly, 0.845 normal.
Right, 0.845 N. But what does that actually mean? If I look at vinegar in the shop, it says like 5%. How do we get from normality to a percentage that makes sense?
Great question. That N is a chemist's unit for concentration, specifically reactive concentration. To get to a percentage, like grams per 100 milliliter, we need one more piece of information. The molar weight of acetic acid.
Molar weight. How much a molecule weighs?
Sort of, yeah.
Yeah.
How much 1 mole of it weighs in grams. For acetic acid, TaCO, let's see, 2 carbons, 4 hydrogens, 2 oxygens. You add up their atomic weights.
Carbon's 12, hydrogen's 1, oxygen's 16. So 2 by 12 plus 4 by 1 plus 2 by 16. 24 plus 4 plus 32, that's 60.
Spot on. 60.00 grams per mole is the molar weight of acetic acid.
Okay, 60. Now what?
Now, acetic acid is simple because it only has 1 acidic hydrogen, 1 titration to give way in this reaction. That means its normality is actually the same as its molarity.
N equals M. For acetic acid in this reaction, yes. So 1 normal means 1 mole per liter. Since 1 mole is 60.00 grams, 1 normal acetic acid is 60.00 grams per liter.
Ah, okay. So Kesser and Steen's result was 0.845 N.
Right. So you multiply that by 60.0000 grams per liter. 0.845 times 60 gives you 50.7 grams of acetic acid per liter.
50.7 grams per liter, that's per 1,000 milliliters.
Correct. Now, to get it into grams per milliliter, we divide by 1,000. So 50.7 divided by 1,000 is 0.0507 grams per milliliter.
0.0507 GML. Still not quite that percentage on the bottle.
Almost there. That percentage on the bottle, like 5%, usually means grams per 100 milliliter.
Ah, so we multiply our grams per milliliter by 100?
Exactly.
Yeah.
0.0507 times 100 gives you?
5.07%.
There you go, 5.07%.
Wow. So Kesser and Steen's homemade Tante Grin apple cider vinegar, from that first titration, it's coming in at 5.07% acetic acid.
That's proper vinegar strength.
It absolutely is, right in the typical range. That's incredible. From apples to measuring density, fermentation, then this careful titration. They've nailed down the exact strength. It reminds me of this one time in the lab, actually. We had this forgotten batch. Just sat there for ages, and it turned into the most intense vinegar. Happy accident, but knowing how to measure it, that was the key to understanding what we even had.
Yeah. Yeah, science helps make sense of happy accidents, too. And we should mention, Kesser and Steen used nice round numbers here for our check.
Right, for the explanation.
But in reality, they plug their actual burette readings, the precise NaOH normality, maybe do multiple titrations, and average them, probably using a spreadsheet for the final super accurate calculation.
Sure, makes sense. But the core insight is that titration lets you precisely quantify that chemical change, that vinegar production.
Exactly.
So from that first density reading of Tante Grin's apple juice all the way through fermentation to the final precise titration, you've really followed the whole journey of transformation and measurement in Kesser and Steen's garage lab. It's just a fantastic example of how accessible science can be, isn't it?
It really is. This deep dive, I think, shows how combining these basic chemical ideas with just careful measurement, it lets you predict things and then check your predictions, even at home.
Yeah.
And understanding these steps helps you appreciate the why behind so many things you just buy or use every day. It's not magic, it's chemistry and process.
It definitely demystifies it. That curiosity like Kesser and Steen have, that's what drives it all. So thinking about that, what other everyday transformations may be happening in your own kitchen or your garden shed could you start to quantify now, just with a bit of curiosity and maybe a few simple tools?
That's a great question to ponder.
Definitely something to mull over until our next deep dive.